some lady should have just told you. Just please make sure you are on mute, and you can have your camera on, camera off, really whatever you want. If you need it at the bottom, you can turn on captions, and there will be automatic captions in English, which might be helpful. What else? We will be taking questions at the end, so please, after when Daniil says that it's time for questions from the people in the audience, then you can either raise your hand by choosing the reactions at the bottom, and you can raise your hand, or you can just put the question in the chat. Either way, we'll get it. Yeah, I think that is all. So I think we can get started. Good luck, and I'll be here if you need me, Danila.
All right, let's just give one more minute for people to join. I'm gonna open up the guiding questions, and we'll start in a moment. I suppose we have everybody now, so I will start. So good day, everybody. Oh, another person is whatever, I'll continue. So today we have a talk from Dr. Kernighan, or if it's all right, I'll call you Brian Kernighan. He is a professor, a very well-established one. He has worked at Bell Labs in the 1970s and onwards, and he has co-worked on the Unix operating system. He has written the book on the C programming language, one of the early programming tutorial books, I suppose. He has also worked on other computing problems, such as the traveling salesman problem, which is used today in a lot of navigational software and such. So he's a very knowledgeable person. And if for any of you who don't know, Unix was a proprietary OS used by AT&T, which later became the basis for OpenBSD, Linux, Mac OS, and Android. So that's one way to connect it to your everyday lives if you are not programming nerds like me. And the C programming language, well, almost every modern programming language and operating system is built on top of C. So it's the foundation of our computing world, I suppose. So Brian, could you, I don't know, share anything more that I might have missed about yourself before I move on to the questions?
Yeah, no, thanks, Demo. And thanks, folks, for all showing up on what I assume is a late Friday afternoon in your part of the world and a nice, bright, sunny Friday morning here. No, I don't think there's a lot more to add. I was at Bell Labs for a long time, starting in roughly late 1960s, and then I came to Princeton, where the professor part of it comes in about 2000. So I've been here almost 25 years. But other than that, yeah, good enough. Thank you for the excessively kind words.
All right. Well, I suppose we can start with the guiding questions now. Just to let everybody know, you can write your questions in the chat or raise your hand, and after about 20 to 30 minutes we will start accepting audience questions, but for now we'll proceed with the guiding questions. So let's start with the first one. How did you choose what you wanted to study after graduating high school? Many high school students after graduating really don't know what they want to do for the rest of their life. So it's a pretty big decision.
Yeah, well, I will tell you, from the perspective of many years later, I didn't have a clue either. And so in that sense, I don't think I was in any way unusual. I went to high school in a very small town in Southern Ontario in Canada. I mean, a really, really, really small school. And more or less by accident, thanks to having a high school math teacher who had an actual engineering background, he sent me to a course at the University of Toronto, or they suggested it. One of these, it was called engineering physics, and it was one of these courses for people who don't know what they want to do. And so it worked out extremely well for me. But I didn't know what I wanted to do. And when I was in that course, at the end of it, this is after 4 years of college, university level stuff, I still didn't really know what I wanted to do. And so I went on to graduate school at Princeton, where I'm actually living now, and still not knowing what I wanted to do much, but it was the early days of computing. And so it was kind of, it seemed interesting, if you like. But there's I think a unifying theme here, which is, I don't know, I didn't plan anything. A lot of things happen more or less by accident. And I guess that's the story of life in some ways, that things happen by accident rather than planning, at least for a lot of people. So that's kind of a long and rambling answer to your question.
And just to clarify, what did you study for your undergraduate?
It was a kind of catch-all course called engineering physics. And so it had a fair amount of real engineering, the kind of thing that you would get for civil engineering, like why are I-beams shaped the way they are. But there was also an awful lot of math and physics and chemistry. The math was almost entirely continuous math, sort that is less useful perhaps than discrete math would have been, but that's the way it was. So very heavy on engineering and then the math, physics, chemistry. So it was a really good, solid background in lots of different things for people who didn't know what they wanted to do.
And you said that by luck, you got into computing and such, since the 60s were kind of the birthplace of the computers. So who introduced you to it? Your professors, or?
I think it was a couple of things. There was at the time, and this was at the University of Toronto, there was exactly one big computer in the whole country. It was an IBM 7094. This is dating me, you realize. But there was one big computer, the 7094, and it was in the building where the engineering school was, so you could physically see it. And then there was a very small computer, something like an IBM 1620, which the electrical engineering department had, and so you could actually touch it. It had a keyboard where you could type, and something that would print, like a fancy mechanical typewriter. And those were interesting, although I didn't do much with them, and I barely learned to program. But I also had a summer job at a local company in Toronto where I got to do some programming as well, and that was kind of fun. So I think it was not that I was doing anything very deep, but just that this seemed like interesting stuff.
I mean, that's a very good way to get into it. I'm better than just saying, oh, I am going to do this, and then discovering you don't like it, but you continue doing it. So you worked the summer job, and you slowly started getting into it, nothing very deep, and then the graduate school. And how did you jump to Bell Labs from all that?
Well, it's another one of these blind luck things. I think when I was a graduate student at Princeton, I got a summer internship actually at MIT. So for geographic calibration, Princeton is less than 100 kilometers sort of southwest of New York, and MIT is in Cambridge, Massachusetts, so call it 200 or 300 kilometers north. So not very far away, really. And I got lucky and got a summer job at MIT in the Project Mac group. This was the group that was working on Multics. They had created this very early, very, very nice time sharing system called CTSS, the compatible time sharing system. And they were doing the Multics system, which was kind of a second system. Let's do everything much better with bigger hardware and bigger software and more people. And I spent a summer working there, basically writing software that would move things from one computer to another, kind of basically. And if I think of it now, it's like one of these commands like tar or zip or something like that. But that was a lot of fun.
So you're porting them basically?
Just basically, it was a program that would collect files from one machine and move them to another where they could be executed test case. And I don't remember any of the details about it at this point. They're completely gone. But that project involved people who were at Bell Labs, which is in New Jersey, as well as the MIT people. And so the next year, the next summer, this would be the summer of 1967, I got an internship at Bell Labs in New Jersey. And again, this would be 50 or 60 kilometers north of Princeton, so quite close, commuting distance. And worked there that summer, had a great time, came back the next summer, had a great time. And then when I finally finished my work at Princeton, they offered me a job at Bell Labs and I took it. And so, but you get this sense of luck, blind luck going on continuously.
Well, I guess it's both blind luck and just like a snowball effect of you get one thing, be in the right place at the right time, you meet somebody, then by chance something else adds onto the ball and like you get it rolling. That's pretty interesting. But I guess a lot of this stuff in life is just being there at the right time.
No, sadly, you're exactly right. You can't predict. I mean, there are ways in which you could perhaps improve your luck by hanging out with the right people or being interested in a lot of things, but it's still pretty random.
Hey, that's why role-playing games are so popular. Roll a dice to make decisions. So things must have changed a lot since your summer jobs programming, because today we have lots of programming languages, although as far as I know, there were also a lot of programming languages in the 70s and 60s. And although, like you said, tar is still used today. If you use either Apple, Mac OS, or Linux, it is often used as a replacement for zip. And but those are console applications. And today, many applications, even if they have a deep backend, they still need to have some kind of graphical element, which I guess is the most visible change in software. But what else do you see that changed a lot since back then?
There's an enormous number of changes, and most of them, I guess, are triggered by the fact that hardware has gotten smaller, cheaper, faster, better, and all, sort of Moore's law in effect applied to all kinds of different aspects of computing technology. And so the flip side of that is because you can get so much more for a certain amount of money, things get bigger. And so all of the things that we deal with today are far bigger than they were, say, 50 years ago, something like that. You're right that there were a lot of programming languages even in the 1960s. Most of those languages have gone away. Today, well, it's hard to say, but probably hundreds, if not thousands of times more languages, many of which are not very much used, but they're still there. Hardware got smaller, cheaper, faster. Memory in particular meant that operating systems became bigger and more complicated. And programming languages proliferated as we understood better how to do things. That's one side. We understand how to create a language that will make certain kinds of programming easier. But we we also didn't have to worry so much about constraints, like constraints on memory and constraints on processor time. So for example, when C was created in the very early 1970s, memory was precious. There was essentially no bytes. And processors were very slow. As that got better, then the language could do more things for the programmer. You could afford to waste, for example, more memory. You didn't have to worry so much about how quickly your program ran on average, clearly not for every program. And so you got things like memory management in programming languages in a way. It's not present in C, but it is present in essentially all languages that people use today. You don't think about it very much unless you get into trouble. And so having lots of memory and somebody look after it for you simplified programming. Having lots of processor time means you don't worry so much about how efficient your particular program is or your particular compiler in creating code, all of those things. So all of that changed. That's one big set of changes related to the increasing hardware capabilities. The other thing that's very different, I would say, from the 1970s in particular, is the fact that networking didn't really exist in those days. Computers were sort of isolated. They talked them only to themselves, perhaps to some peripheral device like a printer, but fundamentally there was no notion, or at least very little notion of networking in the sense that we just take for granted today. And so this combination of networking where you have computers connected to each other transiently, or distributed computing where you have things like data centers where a bunch of computers in, let's call it a physical location, communicate with each other. That simply didn't happen until probably well into the 80s or even the 90s, when the internet became something that was available to the public at large. And so that the set of complications that you have to deal with when you have lots of different computers at lots of different places talking to each other all the time, that's just a different order of magnitude. And that's a place where you really do need more resources and where your programs necessarily get more complicated. I think what's involved in just so that you and I and all of the other folks here can be talking to each other, even though you're in a different continent. And it just works. It's amazing how well it works. So fingers crossed that it will remain working while we continue to talk, but mostly, yes. And so that's the kind of thing that has changed. The scale is enormously different, and so many more people are involved in it. And some of them are technical people, like we guessed everyone here, and some of them are exceptionally non-technical people, but who use this kind of not necessarily understanding what's underneath it, but using it to do whatever they do, whether for their work or for their fun.
I suppose back then it like didn't really exist, people just casually using computers for work, because as I've watched many computer file videos, people had to line up to use the computer at the university. So did you have to like write in advance, like, oh, I need to run this program, give me like 50 minutes, or how did it work?
Certainly in the very early days, before the time sharing came along, or when there were central computers. And when I was a graduate student at Princeton, it was also like that, in the sense that there was a central computer that happened to be the same 7094. The difference was, if the machine was very small, then you might get to use it as a sort of sign-up operation, as you suggested. And of course, professors, important people would get it during the daytime, and unimportant people, like students, would get it in the middle of the night. When the machines got bigger and more powerful and more expensive, then it wasn't efficient to do to do that kind of thing. And so instead you had professional operators, and the machines were in big air-conditioned rooms, and there was a professional staff of operators, and you would hand your computing job to it, usually on a deck of cards, which again, ancient technology. You would hand your job to an operator, the operator would give it to the computer, and a while later you would get results. How long? That could be a few minutes to a few hours to a few days, depending. And so it was a different style of programming. Programs were smaller, they were not interactive, and you were much more careful about mistakes, because a mistake could cost you hours.
That sounds very stressful compared to what we have today. He rewrite a program and run it 100 times and debuggers so we can follow everything along. It
Yeah.
must have been hellish to debug back then.
Well, it was challenging, but on the other, the good side of it, if you want to call it that, was that the programs were small comparatively. And furthermore, they almost always were entirely code that you wrote yourself. So in some sense, it was easier. You didn't have enormous libraries where you had imported 100 different packages, each of which imported their own 100 packages. So you didn't have that kind of complexity to deal with. If you made a mistake, it was probably really your own fault.
Yeah, that is a completely different scale. So I guess moving on to the later years of the 80s and the 90s with the introduction of the personal microcomputer, the Commodore 64, the PET, Commodore PET, Apple II, first computers that, while not incredibly powerful, could easily fit on your desk. And that seems like a very big step up from what you had at university. Did that impact your work?
It's funny, I think that specifically didn't very much. There was an intermediate step or two, which, because of where I was working, was more relevant, I think. And the step was from the big mainframe, this giant computer locked in an air-conditioned room with operator, to what were at the time were called mini computers. And this is things like the PDP-11. And those were small enough physically and cheap enough that they could be bought by a group, not an individual, but a small group of people, like a university department or a research group. And that freed people from the tyranny of a big computer needing a lot of resources and needing people. So you could do your own thing. And so for me, that was probably the big transition, going from the mainframe to the mini computer. And then shortly thereafter came what was, I guess, would be called the workstation. This is thing like Sun Microsystems and so on. And those were fairly powerful machines, but they were actually for individuals. So you could have one of your own, somebody else could have one of their own. They were not cheap, but they weren't super expensive, at the point where an individual technical person doing computer work of some sort would reasonably expect to have one. And then, and this is about, let's call it 1982, the IBM PC came along, and a lot of other computers like the Commodore, which weren't quite as powerful. And those really did become personal in the sense that you could have one for your own personal use that wasn't necessarily anything to do with work. You could have it something to play games with at your home. And so that, again, was another step. For me, it wasn't important, but I think it was important for an enormous number of other people, because in some sense, it made all of this, what interesting things you can do with computing, available essentially to anyone for a fairly modest amount of money, something that literally an individual person could afford. And so, and of course, it didn't need an air-conditioned room, it didn't need operators, all those kinds of things. So I think that's a very important era. But I think of a couple of transition steps in there that would mostly apply to a technical group as opposed to the population at large.
So with those steps, you could basically bring a computer not just to university students and professors, but now business people could have it. Even rich enough families could have it, so where it didn't have to be shared, as you say. And yeah, that is kind of hard to imagine today when all of us have cell phones, which are millions of times more powerful than.
Right, exactly.
Yeah.
I remember, I don't remember the date, but I will guess it was in the 1990s sometime that Compaq, a company that has long since disappeared, finally offered a computer which was the first under $1,000 computer. And it was basically an IBM PC with a 286 or something processor. I don't even remember, but it was less than $1,000, whatever that was worth at the time. And so that genuinely was at the point where you didn't have to even be super wealthy. You just had to have some amount of money, and you could do that, and you could do things with it that might be business, might be your own personal business, or increasingly game-related things. You mentioned the Commodore 64. I mean, I had one of those, but I don't remember doing anything with it except writing these trivial basic programs that would, print hello over and over again. But I think my son used it for playing games with his friends. So
computer gaming, very old, but I guess it drove a lot of people to program. I am pretty sure if there are any programmers here, many of them were probably inspired by computer games to dive deeper into computing. And we're almost at the 30-minute mark. So one last question before we start accepting something from the audience. Let's see, what's a good one? So speaking of new programmers, a lot of new students are very intimidated by the math that they have to learn in calculus and later discrete math. And while I, on an intellectual level, understand that it's very important, even when I struggle with some math problem, I'm like, why do I need this? So, and there are some people who at all don't understand why we need it. Can you maybe illustrate how math has helped you in your career in general? Because for a lot of people, it's just hard to connect the kind of high-level math that we learn with actual technology.
Yeah, no, that's a very, very interesting question. Personally, I was never very good at math, which is something I've heard from every kind of student, regardless of what their field or background is. I was better at math, let's say, than the average person in my high school, which is probably why I got to this course at the University of Toronto. And there was a lot of math there, and we were forced to do it. There was no option. But as you hinted, it was calculus, various flavors of calculus for the most part, complex numbers, all kinds of good things like that, and essentially nothing that was discrete math, and not very much that would be useful in today's computing world, I think. Now, this is grossly oversimplified. It's too bad we're recording this. I have to be careful. But what I've come to think over the years is that some of just the way of thinking about mathematics was probably useful. Some of the general ideas were very useful. The ability to prove a theorem, completely useless to me. And I probably couldn't prove a theorem now if my life depended on it. So it's different. But what are the things that might be useful where somebody might say, oh, I hate to learn this stuff. Why am I doing it? One example would be logic and Boolean algebra, right? You need that kind of thing. For example, something as simple as here's a logical condition in a program, and I need to figure out what's the negation of that. How do I invert that? And it's a trivial kind of thing, but understanding that people wrestled with that back in the 1800s and then finally came up with ways to do it. And that sort of ability to manipulate Boolean things is important. It's important at the lower levels of hardware design. It shows up in your programs to some extent. So that's a trivial example, perhaps, of something where the math, not hard, but really useful. Another one, undoubtedly everybody studies algorithms and sort of wonders why, because a lot of the algorithms, I mean, who cares? They couldn't possibly be useful. I think the thing there is, the important aspect is to understand something about how algorithms differ in how fast or slow they operate. Something simple like the difference between a quadratic sorting algorithm and an n log n sorting algorithm. That's important because if the number involved is big, there's an enormous difference. And so that ability to do just very rough assessments of the order of complexity of a computation is very important. Being able to prove that some particular algorithm has those properties, I'll let somebody else do it. But understanding the difference, particularly between the obvious things like log n and linear and n log n and n squared and 2 to the n, those are important. And understanding that and being able to think about them and to recognize in your program where you need to think about it, that's good. Okay. Something that I got in college and didn't really internalize well enough was basically linear algebra. In linear algebra, the ability to manipulate matrices to do things like transformations of coordinate systems and so on, that's important. You want to do graphics, it really matters. It shows up in machine learning in a wide variety of ways. So that's kind of important stuff. That's continuous mathematics in one sense, but it's also sort of vaguely discrete math. I don't know how you think about it. Machine learning, if you really want to do it, not just plug in programs or libraries that other people have written, but you actually want to think about how to get further with it, you really have to understand, and this is back to continuous mathematics, things like, okay, so how do derivatives work and how do you do symbolic differentiation, how back propagation, what's going on there? All of those kinds of things depend on discretization of continuous mathematics. And then, of course, if you want to do cryptography, that's number theory. And not entirely, some of it's algebra, for example, the field theory, Galois fields, and things like that. Part of it, group theory, that level of algebra, which I wish I had learned better. I got bits and pieces of that in grad school, but not as much as I need. And the other one that I actually learned, and I'm not sure I've ever used, except that it's incredibly beautiful, is complex numbers, which show up all over things like signal processing and other aspects of a place where, again, continuous mathematics shows up in people's lives. So there's a bunch of things where I think, not being able to prove it, but being able to appreciate what it might be useful for, knowing that it is an issue, where you might look for insight, how to assess what other people have done. I think those are examples where the ideas really matter.
That is a good that is a good illustration in general. You covered a lot of ground there, from signal processing to machine learning to I guess even connecting Boolean algebra. We actually are learning Boolean algebra in our class right now in our system fundamentals. And Sergei Titenko in this call, he is our computer science teacher, and we just finished our unit on algorithm complexity. So this is very topical for us right now.
Good. Yeah, important stuff. Learn it.
All right. So we already are having questions in the chat. Somebody has asked a very long question. So wow.
Yeah. I can see the chat window. Let me see if I can make it bigger so I can see it. Do you want me to work down the chat? Do you want to orchestrate it? What would be best for you folks?
Wow. So we could either do it chronologically, or we could start with the shortest. I think doing chronologically is probably the best case here, to be more fair. But since people seem to be asking kind of multiple questions in one, considering our amount of time, maybe we should focus like on the most core of the question, just for time brevity, maybe. But for now, let's start with Ivan's question.
Okay, so Ivan. Yeah. So it's hard to say. I've never really been part of what you might call the software industry, because when I was at Bell Labs, it was a research operation. I mean, it was connected to a very, very large company, AT&T, which provided telephone service, but I never thought of myself as being in industry. And then, of course, for the last 20 or 25 years, I've been an academic, although I don't think of myself as very academic either. I think, however, if we go to your question about this prevailing notion that of the industry being self-repeating, focused on short-term results rather than long-term things, I think that's actually pretty true in a lot of ways, that an awful lot of decision-making in corporations, as I see it as an outsider, seems to be driven by what effect will this have on the stock price in the next 3 months. If they go by quarter, a lot of the money that seems to go into startups and so on seems to be wasted, in a sense, on ideas that just don't seem to make any sense at all, but people are willing to spend, or I would say invest, except it's not the right word. It's more like gamble. Lots and lots of money on things that can't, at least from my standpoint, make any sense at all. What's recent examples? Cryptography, all kinds of cryptocurrency kinds of things. I mean, most of those seem a little better than scams. NFTs, the non-fungible tokens, that's even worse. All of the startups that do things like home delivery of this, that, or the other thing, a few years ago, most of those in some way or other have run into trouble. So maybe what I'm seeing is the visible part, the part that gets all of the press that's reported in the news and so on, and not the fairly steady long-term businesses that are going all the time, but not nearly as flashy in some sense. So let's say I'm kind of skeptical about the software engineering industry and where it's going at this point, and whether what we're seeing with, for example, layoffs in all kinds of companies lately, including ones you've heard of, like Google and Facebook and Amazon and so on, whether this is a sign of at least a temporary change towards something better or different, I don't know. But color me a bit skeptical, a bit pessimistic at this point.
All right, Ivan seems pretty happy with your answer.
Good.
All right, should we move on to the next one by Mitro? Yep. It seems to be about networking.
I don't know that much about the real history of that. I think that there were visionary people who thought about the global network. This would be people like Licklider at MIT, who had the idea of a global network very early in the 1960s. And I think that drove a lot of his ideas about what computing should look like. And of course, in many ways, he was ahead of his time just because the hardware wasn't really up to it at that point. But I think even in the 70s and 80s, networking, as you suggest, was basically kind of mostly aimed at technical populations. This would be people who worked in universities and in the technical parts of universities, or who worked in fairly technical businesses. And I think it just took a long time for that to get going. And part of it was developing the underlying technologies. I don't know that anybody saw really clearly the degree to which something that seems like a technology for very technical people, like the research networks for scientists that you suggested. I suspect most people who were involved saw it that way, and probably most people did not see the fact that it would become so pervasive. In other words, it was quite possible to imagine a global network that would connect scientists, but it was probably much harder to imagine a global network that would connect you and your grandmother. And so it's a completely different thing, and that spread into the general population didn't happen didn't even really begin until the mid 1990s with the development, first of the sort of opening up of the internet to essentially any organization, and secondly, the development of browser in particular. So that things changed at that point. And I guess if I had had the imagination to see that that was coming, I would have invested much more wisely than I did. But but don't take my advice on how to invest money.
I mean, as your example with using the internet to connect you with your grandma, that I'm pretty sure that back in the 80s and 70s, if you proposed that idea of using computers for that, they would have called you mad or even kind of stupid for why would you want to use a computer for that? We have a satellite phone.
I think that there are other examples of that. One that comes to mind, it probably triggered my response here, is that back 100 years ago, it was quite possible to imagine that the cars at the time were very clunky and slow and so on. It was quite possible to imagine that a car could drive, let's say 100 kilometers per hour. Everybody could imagine that, but nobody could imagine that their grandmother would be the one driving it.
That is a good way to put it into perspective. And we've got one more question in the chat about what is the best programming language?
Oh yeah, we could have a wonderful time arguing about that, or at least discussing it. It's not a stupid question, and it's not really provocative. It's an interesting question because, of course, you can't answer it in any definitive way, but it leads to questions about what is important and what are you trying to do with your programming language, or what kind of program do you want to write? What kind of constraints are there on you and on the environment that you're writing it in, and the environment in which the results are going to be used? So if you factor all these things in, it's one of these things where there are lots and lots of components of a vector, and how you weight them determines what your final answer would be. So another way to phrase it, and maybe this is relevant to some of you folks, is, are you learning this thing for the first time? Are you an experienced programmer? What should be taught, for example, in the first programming class at your favorite university? I don't know. I could argue several things. Princeton teaches Java. I don't think that's necessarily the right idea, because Java, although it's a pretty solid language with lots of good things, also has an enormous amount of syntax. And it's just hard to get off the ground in Java compared to Python, which is much easier to use, much easier to get off the ground with, to write interesting things, as a very, very solid, oh geez, give me 1 second. I'm just going to turn these morons off. Yeah, my apologies. I'm getting a spam telephone call from some investment company that wants me to send them money. No, I'm sure this is something universal. Good, he's gone. Okay, I apologize for that, but I had no control over it. Where were we? And just to correct what Danilo says here, Python is not better than Java. It's different. And it does, don't get carried away. It clearly does some things better. And if I were going to pick a language to teach people as the first programming language, and they were probably not going to be professional programmers, they were going to be just average person who might want to use a computer to do something, I would absolutely teach them Python. Yeah, and I've done that in a variety of courses here. If I was going to teach somebody who's going to be a computer scientist, maybe it's better to have something which is more rigorous in the way you have to talk about things like types in the language, where you have to control a structure of a big program, all those things that Python doesn't do as well. If a Java program is written and gets through all of the type checking and so on, it'll probably work properly, aside from logic bugs, thereafter. Whereas a Python program, or there's a decent chance that you will run into some kind of error at runtime that in a more strongly typed language would have been caught at compile time. And so that's depending on the environment, one better than the other.
The reality of engineering, everything is a trade-off, no matter what.
Yep. Yeah, exactly.
But I know that MIT at least used to use computers, structure and interpretation of computer programs, that famous textbook where they taught Lisp as the first one. Lisp is very interesting. I don't really know if people use it today anymore, but it certainly does introduce the concept of programming, I think. Not sure if you have experience with that.
Yeah, they use Lisp, or actually they use a somewhat more modern version of it called Scheme, which differs in a way that I don't really know. And people who are enthusiastic about this find it a very, very natural, intuitive way to write certain kinds of programs, because a program is just data, is just a program. And so it's all very uniform and homogeneous, and you can see how to build complicated things with it. MIT doesn't, I think, do that anymore.
I see.
They are maybe using Python. I'm not absolutely sure of that, which suggests that it wasn't for everybody. I think there's another issue there, and if we push it further, suppose that you were going to teach people a functional programming language. Let's go way off to the end and teach them Haskell or something like that. That's probably a bad idea, because to use Haskell requires a very different and, to me, unintuitive way to think about programming. I think in a concrete, imperative way. I have something here, there's a memory. If I do something, the memory changes. Now I do something else, the memory changes again. And that's, of course, not the way functional languages, and in particular Haskell, would work. Lisp has somewhat the same properties because it's much less imperative than, let's say, C. I think most people, generalization here, I think most people think fairly concretely, fairly not abstractly. And so an imperative language is a better model for the way that people think. And therefore, most people are going to be better able to understand and write useful programs in an imperative language. But it isn't to say that the functional languages or others don't have good ideas. They have some really good ideas. And what happens is that the good ideas in some way get tested, proven out in the context of Lisp or Scheme or Haskell or OCaml, whatever. They get tested there, and the good ideas then get retrofitted into the more conventional imperative language. And so you can see, well, recursion, early thing, that was in Lisp, that was not in Fortran. When I was writing Fortran 50 years ago, it is now part of Fortran, recursion, because it's such a good idea. And so that's a simple example of something that was tested in other languages and then moved into mainstream language. Very, very early example of that. But treating functions as first-class citizens, which again is something that came with functional languages, now an integral part of essentially all of the languages we use every day. Closures, some kinds of pattern matching, lambdas, just the list goes on. So all of these things have been proven out, shown to be potentially useful in kind of languages off to the side, and then find their way into the mainstream. And at that point, they become part of the repertoire. And it takes a while to understand them. I was never comfortable with recursion until suddenly it clicked, and now recursion, what else? How else could you program?
Oh, Taras has a question. Go on.
Hi, Brian. Thanks for joining us. I have a question. You're uniquely positioned, having been at the early onset of computers development, when you went through several revolutions, like revolutions, like computers becoming personal and powerful, the .NET revolution and such. We're standing at the verge of the next big thing, the AI, supposedly. And so I'm wondering, like, you cannot but wonder what this might turn into, right? So computers taking over the world, all the way down to everybody losing their job, to the AI. So on the spectrum of everything, from reasonable to crazy, I'm just curious about, how do you see the AI as, like, how do you see the new thing coming and changing everything? Given your experience with, I'm sure there were a lot of dreams back then, back in the 70s, 80s, 90s, about things that might happen. Some of them came true, some of them didn't. And I'm just curious how that experience helps you to ascertain what the AI might or might not do to the world and the industry. Thank you.
Yeah, it's a great question, and it's incredibly topical at this point. If you think about the large language models, which basically appeared for the general public in December, and at this point, you can't pick up a newspaper article or magazine or something without a story about large language models and take over the world, and we're all going to be out of jobs and so on. I think between, sensible and crazy, I'm or close to the sensible end of things. I think they will have an effect on certain areas, absolutely. And others, it's too early to tell. It really is. Places where I can see them having an effect in my own personal world, it's now the point where you can't ask people to write something in, I'll say English, that is not well specified up front, or you'll just get something that comes from ChatGPT or one of the variations. And what comes from them will sound plausible and may or may not be right. As an exercise, just an amusement, I asked for my obituary a while ago for ChatGPT. And, I was a wonderful person, but they had all of the facts wrong. So I honestly don't think that part of it is going to be, it will change things. An example I have in the class I normally teach in the fall, I ask the students who are very non-technical people, just learning a bit of Python. I ask them to write the program that says, I'm thinking of a number between 1 and 100. Tell me what it is. Simple binary search. I can't ask that anymore because I asked ChatGPT to do it, and it came up with absolutely perfect Python program, complete with really well thought out comments and everything. So I have to do something different. And I think that a fair amount of that kind of thing, and that's good, because that's going to require people to think about, what is the meaning of a good answer to a question, and how much is just echoing and how much of it is actual understanding. So I think that's an area which we don't know, but it's clear we want to change. Another area that I see a lot of my colleagues here are interested in is the effect of AI on various kinds of systems that have an effect on people's lives. Predictive policing is one. If you've got somebody who's done something wrong in the past, can you predict that they will continue to be bad or that they will go straight or whatever? Can you predict in a population what will happen? Where do you focus police resources? There's all kinds of questions like that. And at a simpler level, how do you assess resumes from people? If you're a company like Google, where you get 10,000 resumes a day, how do you assess which ones are promising and which ones you don't want? And of course, which ones were written by ChatGPT. And the problem with those systems, those kinds of predictive systems that are going to affect people, is that they often have an incredible amount of implicit bias, because of the data that they were created from itself has implicit bias based on where it came from, how it was collected over the years, and so on. In the United States, an awful lot of it is racially based. In many parts of the world, I imagine there are gender differences that are in effect encoded in the data that can lead to subtle problems with the results. And so I think that's an area where we really, really don't know what we're doing and don't have a handle on it, and we're going to have to do it better than we currently do. Is it going to put any of you folks out of jobs? Nah. Your job might change somewhat. You may now, instead of going to Stack Overflow, you may ask ChatGPT how to write your code. It will have the same problems, you know. Sometimes it'll be great, sometimes it won't work at all. So I think the bottom line, too early to tell. If I had to make a prediction, I would say that no, the robots will not take over our lives. But they for sure, some parts of this will change parts of our lives. Kind of a waffly answer.
Yeah, I know I'm not qualified to say anything about this, but one of my friends basically said that ChatGPT is like a parrot with a very big ear listening all around the world and just repeating everything it hears.
Yeah.
And it doesn't know what it's saying, but it sounds right.
Yeah, I think that's part of the problem. And then it can be adjusted so that what it says not only sounds right, but is pushing a particular agenda, as opposed to, you know, it's not what it heard, but it's somebody's view of prompting it to something that you want somebody to hear, and that statistically will be used for not good things, as opposed to good things.
And on the topic of machine learning has been used a lot in public as well for statistical calculations, for stocks. Even the YouTube and Google algorithms are also machine learning, just very specific machine learning. So I feel like ChatGPT just put machine learning into the mind of the public, because I don't think the public really thought about machine learning before like last month. So to me, would it be fair to say that it's a trend, that it's a technological trend that people in a few months will probably stop thinking about, just like we stopped thinking about the cloud and a few years back, crypto?
Yeah, I think that's what it is. I think for an awful lot of things, there's something that in the physical sciences is called the Gibbs phenomenon, where you go up very quickly for something, overshoot, and then you come down and you undershoot, and you go back like this, and then you stabilize at some sort of level. And I will guess that the hype about AI will have that same sort of property. That we're in a hype cycle right now. Let's call it on large language models specifically. And then that will go down, and it will come, and eventually will become part of life, and we'll have a sort of a reasonable assessment of what the situation is. There's this consulting company in the United States called Gartner that has a nice curve that looks like that. It's called the hype cycle. And they take a lot of different things like large language models and NFTs and crypto, and they just plot them on a curve of where they are in the hype cycle, which goes from basically up to maximum hype down through a trough of, you know, it's not working, and then back up to something rational. And I wouldn't read too much into it, but it's kind of amusing sometimes to see how their assessments align with your own.
Yep. So does anybody else have any questions that they would like to ask right now? Oh, Denise.
Hello, Mr. Brian. First of all, thank you for your work, and honestly, it's an honor to be able to ask you a question. Thank you for your contribution to the industry in general. You know, I am C++ developer, and I am spent a lot of time with your book about C language. So, and currently, what do you think? What could be the next big thing in the high-tech industry? Where might be the next revolution? Do you have any thoughts about it?
You know, Denise, that's an excellent question. And to repeat something I said before, if I knew that, I wouldn't tell you guys. I'd go and find the right way to invest my modest amount of money and try and become rich. But so
As one of my friends says, if I knew that, I'd be a billionaire.
yeah, exactly.
Yeah.
But maybe I can give you a slightly more serious observation. I mean, we're just talking about where AI and in particular large language models are going. I think some of that actually will be, excuse me, an interesting and potentially useful area for lots of different things. For example, I have a student right now who entirely his own idea is using large language models to improve translation basically of ancient Greek into modern fluent English. I could imagine that kind of language translation that does a better job than, let's say, Google Translate or whatever, because it has a, not understanding, but it has a richer training set, perhaps, of things that belong together. So there, I think there's potential in that kind of area. Absolutely. I'm by no means an expert on that kind of stuff, but I watch what this kid is doing and think, sure, that's really kind of neat. And so I could imagine that there will be a bunch more like that. In fact, he and I are talking at the moment about how I should adjust my course in the fall to have more about this kind of language models so that those will, so that the kids in the class will be better prepared to deal with the world when they get out of school. What else? You mentioned C and C++. I think that, and this is a much more technical kind of area, I think we're not done in figuring out what programming languages ought to be. As we observed earlier, there are a lot of programming languages and they're better or worse for different kinds of things. If I were going off to write software for little tiny devices, IoT kinds of devices, I would probably use C. If I were doing game programming, I might well use C++ because I can build libraries that are a better match between what I want to say and what has to happen underneath. If I were doing operating system work at this point, would I be doing that in C++ or would I be doing Rust, for example? I don't know. Nobody's mentioned Rust before. My first experience with Rust was not very positive, but I started to think maybe it's time to revisit it. And so there's a bunch of areas in and around the fundamental languages that we use that I think are still interesting, even if there are thousands of languages that one might use. And then, of course, the tools that go along to support those kinds of things, integrated development environments. Is VS Code the answer to all of mankind's problems? No. Is it useful? Yeah. So I think there's lots of different things that you could actually play with, and they'd all be useful in the future.
Thank you very much. And one more small question, please. What do you prefer, remote work or office work?
Yes,
Because currently after Corona crisis, almost the whole world switched to remote work, and now currently in Ukraine we also have a war with Russia, and we continue to work due to safety also remotely. But the rest of the world try to come back to the office. What do you think about it?
I prefer an office environment, but with a big extra consideration. When I was at Bell Labs, I had an office, but it was my own office. And it was, I don't call it 3 meters by 4 meters or something like that. So it was fairly big and it was mine, and it had a door and I could close it. When I was an intern at Google off and on for summers, they had big open rooms, and everybody was about a meter away from the next person. And it was too noisy. I found it exceptionally hard to concentrate. And so that was not very productive. So I took to working remotely, but then I discovered I couldn't really connect with the people that I was working with, that it was too hard to make the kind of connections, both technical and informal, those personal connections. And you didn't get that sort of thing where a random conversation would start an idea in your mind or answer a question for you, or all of these kinds of things. And so I think for many reasons, both technical, productivity and so on, but also social, in person is better, but with more flexibility. In other words, maybe not you have to be there 5 days a week. That's deadly, especially if you have to go a long distance. And then, of course, folks in Ukraine are in a terrible, unfortunate situation with a war going on. That just complicates your life. And boy, I hope that gets fixed up soon.
Thank you very much.
As always, it is a trade-off. With a personal office, you might get more privacy and more time to rest and go and talk with people. But with an open office, you get more, I guess, conversation flow. At least that's the supposed ideal of it. A little bit off topic, but I saw that you have an F91 watch. Very nice. Like Casio.
Yeah, mine is the Illuminator, which gets a little brighter. I was talking yesterday, I was walking with a friend in town, and he said, "Oh, my watch is asking me whether he wants to record the walk." And I thought, this is craziness. And so I pointed out that I'm wearing this Casio, which at the moment costs maybe 10 or 15 US dollars. And if I lose it, it costs me another 10 or 15 dollars, and they last forever. And so why would I want a fancy watch, especially if it's going to track me? So I'm glad to see at least one other person who has good taste in watches.
And it tells you the time, it tells you the time of day, it tells you the day, what day it is, Friday, Tuesday, and it has the calendars. So, I mean, what else do you need? I just brought it up because when I watched the AT&T documentary about Unix, all of the engineers in the documentary were wearing Casio watches. So it's just a little bit amusing. And speaking of AT&T and Bell Labs, did you and Dennis Ritchie and Ken Thompson think of your job like as a job, as a 9 to 5, or did you think of it more like as a hobby that also feeds you, I guess?
Yeah, I think it was very much more it wasn't a hobby, it was a job, but it was a job that you really, really, really wanted to do because it was so much fun and you were hanging out with interesting people in an environment that was, really quite nice. And you were paid to do it. So in the most positive sense, it was a job, but one that you probably would have done for free. There was a quotation that your question actually triggered my memory of it. Somewhere in this book called The Mythical Man Month that Fred Brooks wrote, he makes the observation that it's only a very, very lucky collection, a very small collection of people who get to work on something that they would do for free because they enjoy it. Now, you have to eat, you have to, look after a family or something like that, but it's nice to have a job that you enjoy doing and would do, even if they didn't pay you. Yeah. And so certainly Bell Labs was like that, and I know that was the case for Ken and Dennis and pretty much everyone else that I dealt with there. I think you could argue the same thing is true for university faculty, that they're there because they like it.
I guess, as they say, if you find a job you love, you'll never work a day in your life.
Yeah, right. That's the spirit. Yeah.
Does anybody else have any additional questions? I guess I'll continue with some more if we have a bit more time.
Sure.
All right. Let me pull up the list again. And well, on the Wikipedia page for Unix, it says that you coined the name Unix as a joke, as a sort of portmanteau of Multics and something else. Do you remember perhaps what inspired you to call it Unix? Or
Yeah, this is a story that I've told so many times that it probably worn grooves in my brain, and so you don't necessarily have to believe it or not. My memory is that I was standing in the hall outside my office with other people around, like Ken Thompson and Dennis Ritchie. And Ken had created this little tiny operating system, and it didn't have a name or anything like that. And since all of these people had worked on Multics, which was a big, complicated, do everything sort of system, and that's the new version. This new program that Ken had written was very small, did not very much. I suggested that where Multics was many of everything, that this could be called Unix, at most one of anything. And I had, my mental picture was UNICS, because Multics was MULTICS. And so that's my picture of it. And then somebody mutated that, spelled it better, which is a nice idea. And is that true? I don't know. But I think that's more or less the story that's in Wikipedia and related places. I haven't actually looked at the Wikipedia one.
on Wikipedia, it says that you just took inspiration from Multics and called it Unix, and that you don't remember where the X came from. That's what it says on Wikipedia. It cites a 2002 interview of Linux World magazine.
Yeah.
And speaking of which, Linux was named very similarly. It took a look at Unix. They're like, we'll put Linux.
Yep.
So I guess it rhymes. As they say, history does not repeat, it rhymes. And let's see. As you were saying about how it's a job that you really like to do, and that you would have done it for free, maybe. How did you stay passionate? Because currently in the technological sphere, there are so many things happening. You can go into cryptography, you can go into machine learning, you can go into embedded software, there are so many things to do, and everything is constantly evolving, new processors, new computers, we've got new networks, et cetera, et cetera. It's so much new stuff. How do you stay focused, and how do you have passion to continue doing what you're doing when so much around you is happening, when there's so much happening around you?
Right. No, it's a good question. Certainly, when I was at Bell Labs, the field was young. Let's call it, this appeared from 1970 to 1990s or something like that. It was still a young field. And so there was lots of interesting stuff to do, because not many people had done all of this. You tended to know many of the people who were in the field with you and so on. So it was, I think, easier to stay involved in that. But even there, after 25 years in the same place, I started to get restless. And that's part of the reason why in 2000, I went to university. And so it's a different environment now, and I can stay sort of interested in what I'm doing, because every year I get a new batch of students. And so it's kind of like a renewable resource. There's a new group. That's how you think of you guys, right? Renewable resource. And so that's great. Every fall I get a new bunch of people to hang out with who are bright and interesting and so on. And at the same time, the ones who graduate go on to other things still keep in touch. So excuse me. So it's not that you're losing people, but you're always getting an influx of new people. Give me a second. You'd think that somebody who was in the education business could talk 24 hours a day without losing his voice, but apparently not. So anyway, but how do you stay interested in what you're doing? I think you're right that it's easy to think, gee, everything has been done already. The things have been mined out, and so there's nothing new. But I think computing in particular is one of those areas which it applies to so many different things that you can often find something to do in an area, a field where computing is comparatively new in that area, where computer applications are not the central part of it yet. So, for example, for the last several years, I have been hanging out with people in the local Center for Digital Humanities. And that's basically people who are interested in humanities, things like literature and history and classics, architecture, music, whatever. And they're behind in their use of computing compared to, let's say, physicists or something like that. And so these people have really, really interesting data, often very complicated data, and applying computers to it is a new and interesting way to explore. And I'm not doing a lot of that personally, but I'm helping students and faculty members who are interested in that sort of thing. So that's one way to do something that, for me at least, has turned out to be a good way to keep involved and doing somewhat new things, or at least talking to people who are doing new things. Another thing that you can do, if you start focusing just on computing stuff, think about the places where something isn't as well done as it could be. So, for example, we've got manual processes that we use for computing. Can you do something to automate them? Can you create some, well, I start with a shell script and then maybe it becomes a specialized programming language or whatever, something where I was doing something in a clunky way, an awkward way, and now I can do it better by writing some code. That's very small scale stuff, but there's always opportunities for that. And I think that's interesting. One that I would do if I had different physical resources and time and so on, I might start thinking about real small computers like Raspberry Pis and so on. I just never got into it, but that might be interesting. Something else that I think is intriguing is another coffee. Sometimes it's interesting to revisit old ideas with new languages and tools. So, for example, I have a program that I wrote in C originally. What would it be like to write that in Rust? And that would have two advantages. One, it would force me to learn Rust better, and maybe I'd produce something that was actually better. And so maybe Rust is not the right example. Go would be another example where I don't know it as well as I should. Something else that I do, everybody wastes time on some social media. Not you, but most people do waste some time on social media. I spend time on Hacker News, just sort of lurking, and fairly regularly there's somebody who asks a question of, like the one you asked, how do I stay interested in something? Or what could I do in this? Or what are people's hobbies? Or what are their side projects? And I find those things very interesting, because you look at them and you get a breadth of suggestions, ideas, further references. And I find that one of the most interesting parts of Hacker News, that there's something like that, 2 or 3 of those in a week. And so I chase down bits and pieces, and I think that's neat. It typically doesn't go any further than that, but it's a resource. And sometime it might trigger an idea in my mind. So I think that's worthwhile. So that's kind of the way I would think of it. It's mostly kind of paying attention to what's going on. And if you find yourself getting bored with stuff, consciously think about what could I do to become less bored.
So to summarize, try to find fun in the stuff you do. And in general, solving problems is fun. Find a problem that interests you personally and try to apply your knowledge to it. And that should be pretty fun and educational, right? That's to summarize your answer. Pretty much, I guess.
Yeah, and if you can do it for somebody else as well, that's icing on the cake. If you can help somebody else who's got an interesting problem, that's good.
And that's how you get contacts, and that's how you get recommended to work at Bell Labs. Something like Bell Labs. Although I'm not really sure what we have today that might be similar to that. Because, I mean, was Bell Labs like well known? Just to Like, was Bell Labs super well known back in the day, or is it more in hindsight?
Back in the day, it was absolutely well known, certainly in any technical community, because it had produced so many important things. A transistor came out of Bell Labs, for example, and a variety of other technological things like that. Later on, information theory, error correcting codes, so on, those all came out of Bell Labs. So, you know, Nobel Prizes, all of this kind of stuff. So Bell Labs was certainly in any technical community extremely well known. And it had also done a lot of work during the Second World War, war effort on the American side. So yeah, very definitely known, maybe not to the general public, but widely known. So, I mean, the implicit question, I suppose, that you're asking is, what's today's equivalent of that? And the short answer is, geez, I don't know. The Bell Labs I knew kind of mostly isn't there anymore. The company that it was part of was fragmented, was, you know, in many ways damaged by technological improvement that they didn't keep up with in a lot of ways. There is still a Bell Labs, they still do interesting work, but it's not on the scale that it was when I was there 50 years ago. Today's equivalent, I don't know. The big tech companies, specifically, I would say Microsoft and Google, do have interesting research going on. They do work on a wide variety of topics, perhaps not as wide as Bell Labs was. I would guess less on, you know, real hardcore physical science like semiconductor physics, which Bell Labs did, or fiber optics, which Bell Labs did. But they have at least a breadth of that, but probably moved up the stack. So both Microsoft and Google have that kind of thing, and probably others. I think of IBM as another option, but perhaps more development than pure research, but underneath it, there's got to be a component of exploring where you don't actually know where you're going. And then there's probably other places that I have forgotten.
I suppose in this case, we just have to discover our own Bell Labs, or if somebody wants to create a research group, create our own. But the future always holds something new. So who knows, maybe we'll see another research group which does software, hardware, and everything in between, and combines many brilliant people together. So I think it's time for us to wrap up. If anybody has any small questions, ask it right now. If not, we can wrap up. I suppose that's it for today then. Thank you very much. Do you have any closing statements, I suppose?
Yeah, no, I just want to say thank you very, very much. I really appreciate the chance to talk to you. And it's one of the good things about modern technology. It's actually feasible to talk to somebody who's a long way away. And so I greatly enjoyed that. Danilo, thank you for orchestrating all of this. And thank you to the rest of you for good questions and all the rest of it. So, and the sign here says your Mac will sleep soon unless plugged into a power outlet. So timing is perfect, ladies.
Have a great day, and I'll keep in touch.
Okay, excellent.
Bye-bye.
Thank you.
Thank you very much.
much.
Goodbye.
Thank you, bye.
Have a nice day.
Thank you.